So in this module 13 here, okay, you will learn about the interfacing the ADC. Okay, so there are few what we call here subtopic here, which is first we are looking at the introduction of ADCs. Okay, you need to know what is ADC, what are the criteria that needs to have before. Okay, you interface your ADCs, and then after that you are looking at the how to program the analog to digital converter. Okay, which is we're going to convert from analog signal to digital signal. How to do programmings. Okay, which port that we're going to use in order to read analog signal from the sensors and put it to your process it to your microcontroller. And then after that, we are looking at the DSC, which is a digital to analog converting, okay, programming. And last but not least is sensor interfacing. But in the sensor interfacing, if not mistaken, we'll not cover much on this part here. Okay, you can read it by yourself. Okay, so let's look at the introduction part of the what we call here analog to digital converter. So this is the ADC device. Okay, so analog to digital converter, or sometimes we know it as ADCs, are amongst the most widely used device for data acquisition. Okay, means that since the signal outside in our real world, is in analogs. Okay, so but the CPU or your processor must process the data in the binary number or digital number, which is in the discrete signal. So what you need to do is you need to convert the analog signal first to the digital signal. Then after that, you can do the processing part. And of course lah, after you do the data processing, change it to the digital signal. Then in order to display the signal to the outside world, okay, in the real world, we need to change back to the analog signal. Okay, because all of the our real world is in the analogs. Okay, so digital computer use a binary, which is a discrete time signal, but physical worlds, everything is an analog signal, which is it is a continuous signal. Okay, those device called a transducer, okay, which is sometimes we call it as a sensor, is needed to convert these physical quantities. Okay, so in order to convert these physical quantities, okay, what you need to do is you need to have a transducer, or sometimes you need to have a sensor, which is this sensors here will uh, try to capture or try to convert the continuous signal to electrical values, sometimes voltage or current. And from this voltage or electrical signals here, then after that, you can change it to the discrete time signals. Okay, so these physical quantities are such as temperatures. Okay, if you're going to take a temperature measurement, so the physical quantity is a temperature, and pressure. If you're going to read what is the pressure of the certain uh, places or certain box examples, okay, and then we have uh, etc. And this physical quantities then after that will be converted to the electrical signal, which is in the voltage or in a current, okay, by this transducer or sensors. Then after that, okay, so you see here, this is your sensors, okay, from the analogs here, okay, you have a continuous signal captured by the sensors. This sensor will convert this analog signal to what we call here to this voltage or current, which is in electrical signals. Then after that, this electrical signal will be converted to the discrete time signal by using the ADC. Okay, and ADC, okay, this digital signal then after that can be processed by the CPU, because the CPU need to process in digital signal, which is in the discrete numbers, okay, which is in a binary representation. So after the data manipulation, data processing done, then after that it will display back to this display. This is the output, which is before we go into the output, need to have another circuit here called a digital to analog converter, and after that we can display it to the output. So this is a microcontroller connection to a sensor via ADC. Okay, so what this ADC do? ADC is used to translate the analog signal to a digital signal, or sometimes we can call to convert from analog signal to a digital signal. Okay, then now we are going to look at a few ADC characteristics. Okay, before we go more details on the how to do the ADC programming. Okay, so you need to know the ADC characteristics. What are the ADC characteristics in ATmega 32 particularly? Okay, so in ATmega 32, an N-bit ADC is used to translate the analog signal to digital signal so that micro P can read and process them. Okay, so ATmega 32, okay, the size of ADC is depending on every chip. Okay, sometimes contoh if sometimes A chip have a 10-bit ADC and B chip, for example, have a 12-bit ADC. So this N-bit ADC is very important lah to what we call here to determine what is the resolution of that ADCs. Okay, and some of the major characteristics of ADC that we need to know are first the resolution. Okay, so ADC has an N-bit resolution, which is sometimes we have a 8-bit ADCs, which is 8-bit resolution, 10-bit ADCs, 12-bit, 16-bit, and etc. Okay, so this is depending on the chip itself lah. Okay, for ATmega 32, okay, so the number of resolution is 10-bit. Okay, so the higher resolution ADC will provide a smaller step size, which is a smaller change can be recognized by an ADC. Why? Because if you can see from this table here, this is the resolution versus a step size for ADC with a VREF of 5 volt. Okay, how to calculate the step size? By using this formula here. Okay, which is the VREF divided with the number of step. How to get the number of step? This number of step is depending on your bit, okay, the size of your, the resolution of your ADC. Okay, if you have n-bit, 8-bit ADC, so the number of step is 256. How to get 256? 2 to the power of 8 is a 256. So what is the step size? Okay, the step size is 5 divided by 256 equal to 19.53. So means that every bit, okay, from 0 to 256, okay, so if you increase the bits, okay, the number, the steps here, okay, for example, from 0 to 1, okay, the size is 19.53. Okay, and if you millivolt, this is in millivolt. Why millivolt? Because the VREF is 5 volt. Okay, so every increase of the number of steps, okay, it will increase about 19.53 millivolt. Okay, if you total up them up to, okay, 19.53, you total them up, you will get 5 volt, which is 19.53, you darab dengan 256, you will get 5 volt. Okay, so this is for the 8-bit lah ADC. Okay, if you have a 10-bit ADC, all right, so the number of step is a 2 power of 10, which is 1024. And you see here, the step size much smaller, okay, becomes smaller with the higher resolution. So means that, okay, you have more accurate every time you do the ADC converting, okay, because the step size becomes smaller with every increasing. All right, so if you have a 12-bit, so the number of steps is 4096, and the step size is 5 divided with the number of steps, then you get 1.2 vote. Okay, so although the ADC resolution is fixed, but the step size can be controlled by VREF. Okay, because every time you buy your chips, okay, this resolution here, okay, the size of this ADC is already fixed. Okay, if you buy the Atmega 32 and Atmega 32 is a 10-bit ADC, so you cannot change the resolution. Okay, what you can change here is the VREF. Okay, either you're going to increase the VREF, decrease the VREF in order to get the smaller step size. Okay, so that is step number one, characteristic number one, which is the resolution of the ADC. Okay, then with number two, okay, we were going to look at the conversion time. Okay, what is the conversion time? So conversion time is a time ADC takes to convert from analog input to the digital number. Okay, you can see from here, this is your analog input. And then from here, to convert to this binary data output, so this is the time taken, okay, to, okay, once the conversion has been started, okay, until it finish producing this binary data output. That is what we call as a conversion time, which is time taken to convert from analog input, okay, from read the value from the sensors and producing the binary data output, which is a digital numbers. Okay, then we have the characteristic number three is a VREF. Okay, so VREF is an input voltage used for a reference voltage. So this is the VREF. So this VREF here is used to determine the step size. Okay, if you have a larger VREF, then your step size will be much higher lah. Okay, if you have a smaller VREF, then the step size is smaller. Okay, so this VREF is your voltage reference lah. If you put 5 volt, okay, the maximum value of your conversion here is from 0 to 5 volt. If you VREF is 10 volt, then the conversion will vary from 0 to 10 volt. Okay, so the voltage connected to this pin along with the ADC resolution will dictate the number, the step size. Okay, and then characteristic number 4 is a digital data output. So in an 8-bit ADC, okay, we have a 8-bit digital data output from D0 to D7. Okay, so this is the output lah that will produce here. Okay, depending on the ADC itself. Okay, sometimes we have a 8-bit ADCs of which is produce 8-bit digital data output, and sometimes we have a 10-bit produce 10-digit binary data output. Okay, so how to calculate the D out? D out, okay, to get the D out equal to V in. Okay, so V in is your voltage input lah. Okay, for examples, because I cannot counting, so it hard to. Okay, number one. Okay, so let's say you have a V in is a 2.5 volt. Okay, so you're going to find out what is the digital output for this 2.5 volt. Okay, so how to get the digital output for 2.5 volt, which is a representation of the binary output here is, okay, you just use a V in bahagi dengan step size. Okay, how to get the step size? Okay, let's your VREF is 5 volt. Okay, so 5 volt bahagi dengan 8 bit. Okay, so you will get the step size. Okay, which is 5 volt bahagi dengan 256, you will get 19.53 millivolt. Okay, so now from here, V in is 2.5. Okay, so 2.5 divided with 19.53 millivolt. Okay, you will get 128. Okay, so 128 you convert to binary. Okay, So, that's for 128 convert to binary representation. Then the digital output would be 10000000. So that is for the 2.5 Vin. So the representation of the digital output is 10000000. Okay, so this is how to get the digital data outputs. Okay, so now let's look at these examples here. Okay, so you have a 8-bit ADC. Okay, your ADC is with a resolution of 8 bits, and the reference voltage is 2.56. Okay, you're going to calculate what is the digital output. Okay, from D0 to D7. If the analog input is 1.7 volt and 2.1 volt. So this is the inputs lah. Okay, the analog input sensed by your sensors. Okay, they are measured by your sensor, and then you're going to find out what is your digital output. Okay, so what you're going to do here is, okay, first, okay, we're going to find out what is the step size. Okay, how to get the step size? Step size sama dengan Vref bahagi dengan, okay, here, the number of step. Okay, since you have a 8-bit ADCs, okay, the number of step is 2 power of 8 is a 256. Okay, so 2.56 divided by 256, you will get 10 millivolt. So this is the step size. Okay, so now you're going to find out what is your digital output by using this formula here. Okay, D out sama dengan V in divided by step size. Okay, since the V input, okay, that measured by the sensor is 1.7. So 1.7 divided by step size, okay, which is 10 millivolt, okay, then you will get 170 in decimal. Okay, so this is a dalam decimal. Okay, you need to convert to binary. So 170 convert to binary, so you will get 10101010. So means that 1.7 is equal to, okay, the digital output for 1.7 volt is represented by 10101010. Okay, so this value here will be come out from this binary data outputs. Okay, after you did the analog to digital conversion. Okay, so and the second examples here. Okay, let's your input the voltage measured from your sensor is 2.1 volt. So you're going to find out what is the digital output for 2.1 volt. Okay, so sama juga. So what you're going to do is 2.1 volt, which is your V in, divided with a step size. Okay, the step size is 10 millivolt, and you will get 210. Okay, so this is in decimal. Okay, so you convert from 210 to binary representation, and it will give you 11010010. So this is the value, the digital output that will represent with a 2.1 volt from your sensors. Okay, so this is how to get the digital output based on this formula here. Okay, now we're going to look at the fifth characteristics that you need to know is the parallel versus serial ADC. Okay, so we have two types of this ADC. One is a parallel ADC. The second one is a serial ADC. So parallel ADC is a 8 or more pin dedicated to bring out the binary data. Means that you have all the binary output will be sent out, okay, parallelly. Okay, while for the serial ADC, only one pin for data out. Okay, for examples here. Okay, now you're going to, okay, you read this value here from your sensors, and then if you're, what we call here, if you're using a parallel ADC, so this D out here will be displayed, okay, on this side here, okay, parallelly. Okay, so you will get 10 10 10 10. So this is that coming out from your D out. Okay, so this is a channel 1. Channel 1 is your ni lah, where you need to put your sensors. This is your input, and this is where the output will be produced. Okay, and let's say if you have a serial ADC, only one pin for data out. You see here, you have channel up to 7, and this is the D out. So what happened here is, if you put a sensors here, and the sensor reads out 1.7 volt, and the D out here will be this value here. Okay, 10 10 10 will come out from this D out. Okay, 1 bit at a time. Okay, mula-mula dia akan hantar, depending lah, either you're going to send out the most significant bit first or least significant bit. Okay, if you're going to send out the least significant bit, okay, the first cycle 0 will come out, then after that followed by 1 0 1 0 1 0, and lastly is on the 8th cycle bit number 1. Okay, so this is how the parallel versus serial ADC. Okay, the first one here, the parallel, means that you send out the D out, okay, all bits at the same time. But for this one here, serial ADC, 1 bit at one time. Okay, and then we need to know about the analog input channels. Okay, so many data acquisition application need more than one ADC. Means that if you have many sensors, okay, to convert to read out the values, so you need to have more than one channel. Okay, so this ADC chips, okay, will come up with a sometime with a 2 ADC channels, 4, 8, or 16 channel on the single chip. So this is depending on the chips that you're going to use lah. Okay, sometimes that particular chip just comes with a 2 analog input channel. Means that you can put 2 sensors at one time, cannot more than that. Okay, if you have 4, then you can put 4 sensors to do the analog to digital conversions. And last but not least is successive approximate ADC. So this is widely used to convert analog input to digital input, and this has 3 main components, which is successive approximate register, which is a SAR, comparator, and control unit. Okay, so this is for the ADC characteristic. Okay, any question up until here? Ada soalan tak? Okay, if no question, then we move on to this slide here. Okay, which is okay how to do the ADC programming. Okay, macam mana nak buat ADC programming. Okay, before we go more details on ADC programming, how to do a ADC programming first. Okay, you need to know the ATmega 32 ADC features. Okay, we need to look at what are the features available in ATmega 32. So ADC peripheral of ATmega 32 has the following characteristics. Okay, first, okay, the resolution, okay, for ATmega 32 is a 10-bit ADCs. Okay, so dia ada 10-bit ADCs. So 10-bit ADCs, what is the step size? Okay, so you can come up with this lah. Mula-mula kamu dapatkan dulu dia punya number of step, which is 2 power of 10, you will get 1024. And then the step size, you need to divide it with the VREF lah. Okay, VREF divided with a number of step, then you will get the step size. Okay, so ingat, ATmega 32, it is a 10-bit ADCs. Okay, so the digital output also 10-bit lah. So kamu akan ada daripada bit 0 sampai bit 9. Okay, and it has a 8 analog input channels. So ada a total of 8 analog input channels. Okay, so you have 8 analog input channels. So this 8 analog input channel will be placed on port A, if not mistaken. Okay, later we will see more details. Is it port A? Yeah, port A. Okay, and then with a 7 differential input channel and 2 differential input channel with optional gain of 10 times and 200 times. Okay, later we'll see, okay, what is the single input channel, what is the differential input channel. Okay, and number 3, okay, the converted output binary data is held by 2 special function register. Okay, after you do the D out, since it is 10 bit, okay, one register only consists 8 bit data. Okay, since it is a 10 bit, so kamu kena ada a total of 2 registers. Okay, to accommodate this 10 bit. Okay, kalau pakai satu register tak cukup. Okay, which is you have a remaining 2 bits more. Okay, so you need to have 2 registers, which is we call it as a ADCL. Okay, so this is a ADC low and ADC high. Okay, for the ADC result high. Okay, to accommodate this 10 bit ADC. Okay, since your digital output, okay, we can see here, this digital output is from D0 to D9, okay, which is 10 bit. So that's why you need to have an ADC low and ADC high. So ADC low will consist from D0 sampai D7, while ADC high is from D8 sampai D15. Okay, but ADC high we only use the from D8 and D9 only. Okay, the remaining of the bit will be unused bit. Okay, sorry tak dapat nak lukis hari ni. Alright, and then since ADCH and ADCL give a 16 bit, okay, so ADC data out only 10 bit. Kenapa? Okay, at Mega 32 only 10 bit ADC. Those remaining 6 bit will be unused. Okay, as I mentioned earlier, okay, since we have only 10 bits, so remaining of the 6 bit will become unused bit. Okay, so there are 3 options for the VREF. Okay, the first one here is the VREF connected to AVCC. The second one here is the VREF use an internal voltage, which is 2.6 volt. And the third one is external ARF pin. Okay, later we'll see, okay, how to connect, how to sambungkan, okay, the ADC, okay, either to use the VREF, internal 2.6 volt or external RF pin. Okay, and number 6, the conversion time detected by crystal frequency connected to external and the ADPS0 and until ADPS 2 bits. Okay, later we'll see how to detect the crystal frequency. Okay, so that the external, okay, the frequency of ADC conversion is below a certain value. Okay, if bigger than this value here, what happened here is the accuracy of the conversion will become less. Okay, so you need to make sure lah. Okay, you need to put a prescaler. Okay, which is here in this bits here, you need to put a certain prescaler in order to make sure that your ADC is working below a certain frequency. Okay, if bigger than that frequency, what happened here is the accuracy of the conversion will become less. Okay, so this is kita recall back, this is at Mega 32 pin out. Okay, and by looking at this port A here, okay, you see this port A, you have a total of 8 ADC channel, okay, which is ADC 0, ADC 1, ADC 2 until ADC 7. So this is where you need to put your sensors in order to convert from analog inputs, okay, to digital value. Okay, so all of the sensors, transducer must be connected to port A. Okay, so this port A here, instead of using it as an input-output port, this port A also can be used as a analog to digital conversion. Okay, and this is a ADC connection and programming. Okay, so this ADC use an inductor and capacitor in order to get a stable voltage source to the AVCC pin. Okay, so make sure that your ADC, your AVREF ground and AVCC at this pin here, pin 30, 31, 32 must be connected to this inductor and capacitor. Inductor and capacitor, to get a stable voltage, and this will become your AVCC. Okay, so in ATmega 32, there are 5 major registers that are associated with ADC. So these 5 registers you need to know lah. Okay, the function of this register. Okay, we have the ADCH and ADCL. Okay, so the ADCH is a high data to store the result of high value, and ADCL to store the result of a low ADC. Okay, so this is where you're going, where the CPU store the result after conversion. Okay, every time you do the conversion, after the conversion is finished, the result of the digital output will be stored inside of this ADCH and ADCL. Okay, so next we have the ADCSRA. Okay, so this is a ADC control and status register. So this is where you're going to do your settings. Okay, all your settings must be done inside of this ADCSRA. Okay, then we have a ADMARC. So ADMARC is a ADC multiplexer selection register. So this ADMARC also need to be settings lah. Okay, depending on. Okay, so the things that you can put inside of this ADMARC is what is the VREF that you're going to use, the EDLA. So this EDLA, because this EDLA is used for how to store the data inside of this ADCH and ADCL. Either you're going to put it in left justified ataupun right justified. Why we need to put, we need to do the settings, on the EDLA. Okay, either is a left justified and right justified. Because why? Because this, when you combine ADCH dengan ADCL, the number of bit is 16 bit. But for ADC ATmega 32, you only need to have a 10 bit. So you need to make sure lah, either you store the value inside ADCH, ADCL by using a left justified ataupun right justified. Okay, and next is this one, SPIOR, SPIOR, which is this is a special function of IO register. But on this module here, we'll not cover more on this. But we're only looking on this registers here. Okay, so now we are going to look at the ADMARC registers. Okay, so this is your ADMARC register. ADMARC register have 8 bits. Okay, so mula-mula kamu akan ada Mark 0 sampai Mark 4. Okay, so this we call it as a Mark 4 to 0. Okay, so this is an analog channel and gain selection bit. So from this bit here, bit 0 until bit 4, this is where you need to pilih. Okay, you need to select your ADC channels. Okay, either you're going to make it as a single-ended ataupun differential channel. Okay, and then we have this EDLA here, this bit here. Okay, so this bit is very important lah. Okay, so you can see here this ADC. Okay, when you put value here, it will put your result inside of ADCH and ADCL as a left justified. Okay, if you see here, this bit will detect either the left bit or the right bit of the result register. ADCH and ADCL are used to store the result. Okay, if you write 1 to EDLA, so what happened here? Okay, you put it as a left justified. If you put a 0 here, your value, your digital output, okay, the result of the ADC conversion will be put to your ADC register as a write justified. Okay, and last but not least is this one, ref 0 and ref 1, bit 7 and bit 6. So this is a reference selection bit. Okay, so this is very important. Okay, there are three options for VREF selection. Okay, which is you're going to take a AREF pin ataupun AVCC pin ataupun internal 2.56 volt. Okay, so how to select this VREF here? Okay, so to select this VREF, you can do a selection. Okay, you can do a setting on this bit here, ref S0, ref S1. Okay, so this is the value dah. If you put 0, 0, what happen here is your VREF will come from the AREF. Okay, so here you can see here. Okay, VREF akan datang dari pin nombor 32, which is your AREF. Okay, if you put value here is a 0, 1. Okay, you put 0 and 1 here. What happened here? The VREF will come in from your AVCC. Okay, so here you can see the AVCC is this pin lah, 30. If you put 5 volt to this AVCC, so what happen here is your VREF automatically become 5 volt. Okay, so this AVCC pin is the same as VCC lah. Okay, depending on your VCC. If your VCC is 10 volt, then your VREF become 10 volt. And when you put 1, 0, okay, so this is a reserve lah. Okay, 1, 0, reserve, and 1, 1, what happened here is you use the internal 2.56 volt. Okay, so this is a value already been fixed lah, regardless of the VCC. Either you use a VCC 10 volt, 5 volt, 12 volt. Okay, these settings here will always produce a 2.56 volt for the VREF if you put 1, 1 to this bit. Okay, and this VREF, macam yang kita lihat sebelum ni, this VREF will determine the step size of your ADC. Okay, because step size formula is VREF divided by number of steps. Okay, any question up until here? Okay, if no question, then we go to this bit here. Okay, from max 0 until max 4. Okay, so what this max 0 and max 4 do? Okay, so the max 4 until max 0 in add max will determine the analog channel and gain selection to be used. Okay, since at mega 32, okay, the total of analog channel you have is 8 channels. Okay, from ADC 0 dekat PA0 and then ADC 7 dekat PA7. Okay, and then this ADC channels here will be connected to this multiplexer here, in which this the multiplexer will determine either you use the single-ended ataupun differential input. Okay, so here if you can see here, okay, so either single-ended or differential input can be selected to be converted to digital signal. Okay, if a single-ended is selected, okay, you can choose input channel amongst ADC 0 to ADC 7, which is single pin is used as an analog line and ground as a common ground. Okay, contoh. Okay, you're going to have a single-ended input saja. Okay, and your sensors is connected to channel 0, ADC channel 0. So what happened here is, okay, upon you do a programming, okay, you need to put make sure that max 4 to max 0, the value is 0, 0, 0, 0. Then what happened here? Okay, now the CPU will take value from this ADC channel 0. Okay, If you put your sensor at ADC 1, so you need to make sure that you write down this 0, 0, 0, 1. Okay, if you put your sensor on ADC 7, so make sure that on your programming, okay, under this add marks here, add marks register, you need to select 0, 0, 1, 1. Okay, if you put your sensor at channel 7, but when you do the settings, okay, you do a setting for ADC 2, okay, which is you put 0, 0, 1, 0. So what happened here is whatever value coming from channel 0, channel 7 here will not be processed to do the analog to digital conversion. Okay, so only value from this channel here will do the will go to do the ADC conversion. This is for the single ended inputs. Okay, and this is the if you're going to use a differential input. Okay, if differential input is selected, okay, you can choose input channel as well as the op-amp gain, either multiply by 1 with no gains, with a gain of 10 times, or gain of 200 times. So this is the selector. Okay, and this is where you need to put your sensors. Okay, there are, and this is the positive differential input, and this is a negative differential input. Okay, make sure that the positive of your sensors goes to this channel here, and the negative will go to this channel here. Okay, so this is how to get the differential inputs. Okay, and most of the time kita akan guna yang ni lah, single ended input, unless you're going to opt for the differential input with a gains. Okay, if you're going to if your sensors, okay, the analog input is too small, then you need to do a you need to amplify the inputs. So you need to use this differential input with a gain. Okay, either you're going to multiply with a 10 times or 200 times. Okay, and last but not least is a EDLA lah. Okay, so this EDLA, okay, under this add marks here, which is bit here, bit number 5 here, will determine, okay, either the left bit or the right bit of the ADCH ADCL register used to store the result. So this is your ADC. Your ADC is a 16-bit, although we only use a 10-bit for Omega 32. Okay, so you have the ADCL for the lower byte, ADCH for higher byte. Okay, since we only use the 10-bit for the ADC, okay, so what happened here is 6-bit will be, the remaining 6-bit will become an unused bit. Okay, how to make sure this unused bit here, either you're going to put it on the right or on the left. Okay, if you put the EDLA with 1, means that it is left justified. Okay, so all the result will be placed on the left side here. Okay, which is the whole ADCH will be have this bit here. Okay, the result which is bit 9, 8 until bit 2, while ADCL, okay, this bit here will consist of value from D0, digital output 0, and digital output 1. Okay, while remaining of the bits from bit 0 until 5 here will become an unused bit. Okay, so this is how the result of the digital output after the conversion is being stored lah. If you put your EDLA equal to 1. Okay, if you put the EDLA equal to 0, means that you're going to store the result in the right justified. So means that all the result will be stored on your right hand side, while unused bit on the left hand side. So means that D0 until D7 will be stored inside of the ADCL, and D8 and D9 inside the ADCH, while remaining from bit 10 to 15 is an unused bit. Okay, most of the time, okay, we're going to use this EDLA sama dengan kosong lah, which is a right justified. Okay, unless you're going to change to left justified, so you need to put a setting, okay, give a 1 to your EDLA and inside of your add marks register. Okay, and then we have this ADCH and ADCL register. So ADCH, ADCL register are used to store the result after the analog to the digital conversion is complete. Means that all the digital output after the conversion, okay, will be stored inside of this ADCH and ADCL. Okay, make sure that okay you take the 10-bit only from this ADCH and ADCL. Why? Because at Vega 32, the resolution size, okay, is a 10-bit ADC. So only 10-bit, okay, will consist a valuable information. Okay, a valuable information from the conversions. Right. So this is for the ADCH and ADCL register, and then we have the ADC SRA register. Okay, so this is where you're going to see the status and control the register of ADC. Okay, so ADC SRA also have 8 bits. Okay, so 3 bit for ADPS 0 sampai ADPS 2. So this is for the prescaler lah. Okay, all the prescaler you need to set on this bit here. And then we have this ADIE here. So this bit 3 here, this is for ADC interrupt enable. Means that, okay, if you're going to do analog to digital conversion by using the interrupt method, okay, you need to enable this bit here, ADIE. If you not enable this bit, what happen here? Your analog to digital conversion will only use a polling method. Okay, kalau nak guna interrupt method, make sure enable this thing. Okay, then this bit here, ADIF, bit number 4, this is for the ADC interrupt flags. Okay, so this bit here, this is for the status only lah. Okay, we no need to put anything here. Okay, so this is only for the status, which is this bit is set, okay, akan jadi satu when ADC conversion completes and the data registered are updated. Okay, after the conversion is complete and the data register, okay, all the result has been placed to ADCH and ADCL, then this flags here, okay, this bit will be set, okay, to let the CPU know, okay, we already finished doing the conversion. Then after that, okay, so this is for the interrupt flags lah. One is a 1, so the interrupt will trigger. Okay, and then we have bit number 5, okay, for the edit. Okay, so this is auto triggering of the ADC is enabled when you set this bit to 1. Okay, and we have the ADSC. Okay, so this is most important lah. Okay, this is the second most important. Okay, every time you're going to start the conversion, you need to put 1 to this ADSC. Okay, means that if you put 1, the conversion will started. Okay, if put 0, what happened here? No conversions. Okay, there is the conversion is stopped. So every time you're going to start the conversion, you need to set this bit 1. And last not least, this bit here, this is super important. Okay, which is this is where you're going to enable the ADC. Okay, so when you put 1 here, means that okay, you enable your ADC. If you put 0, even though you put ADSC here with 1, so the ADC conversion will not happen. Why? Because you disable this bit here. Okay, so make sure every time you're going to do the ADC analog to digital conversion, make sure you enable this bit, and then after that you can start by putting 1 to this bit here, ADSC. Okay, any question up until here? Okay, in the next class, okay, we are going to look at this prescaler. Okay, how to set this prescaler, because we need to make sure that, okay, the clock frequency is less than 200 kilohertz. So every time you need to do ADC conversion, make sure that the frequency your exter is less than 200 kilohertz. How to make sure your clock frequency is less than 200 kilohertz? Okay, by setting this prescale kat sini. Okay, dekat mana? Dekat ADC SRA under this bit here, bit 2 until bit 0. Okay, so next class we will looking on this slide here. Any question up until here? Ada soalan lagi? Ada soalan tak?